Hello and welcome to the KIM Resurrection Series Part 11. In this episode we'll be plugging in a substitute ROM and RAM board. Here, as we can see on the screen, is how I'm going to decode everything. We'll have a 74138, just one of them, and that will be generating the K0 to K7 signals, which is K0 being the lower 1K of RAM, 7 being the 7th 1K of RAM up from the bottom, and 5 is in between. Now the idea here is to use the onboard RAM because we know the RAM on the KIM board is damaged. I haven't replaced that yet. Still wait until I've finished other things first because I know this RAM is good that I've got on this plug-in board. Then we'll have the K7 will go to the ROM chip on this plug-in board. So it would be running not the ROM that's on the RIOT chip, but what's actually plugged in. And then we've got the K5, which shows Wi-Fi. That's Wi-Fi from the chip, but that's actually the K5 signal. And what I should do is I shall feed that out to the AK signal, which enables the onboard memory decoding. The idea of that is we can still use all the peripherals that are actually built into the cloned RIOT chip, which needs the Wi-Fi signal. I haven't done the Y6 because we shouldn't be running anything on the second RIOT chip because that just deals with the teletype and the cassette interface. If we go to that chip, it just won't work. The board I'm using is an old one. It needs a bit of modifying at the back. So what we're going to do is, this is the circuit for it. We'll just be using this one decoder chip here, which has got A, 10, 11 and 12 on it. Exactly the same as the one that's on the KIM board already. And here we've got Y7 coming out, which is K7. Already goes to the ROM chip, so that's good. And then we've got the Y5 coming out. That is what we need to feed that down to this KA signal to enable the address decoding on the KIM board. And we also need to connect this Y0, which is for the RAM, across onto the RAM board. So we don't need either of these two ICs. What we need is to relink across from there to there. I know that says Y7, that's a different Y7. So we put a link from here, comes across here, and that feeds up into the RAM. Because this IC won't actually be installed, so this pin doesn't actually go anywhere. And we also need to connect between here and here. So that wire there comes up and out of the K5. So the K5 feeds direct to the KA signal to enable the onboard decoder. So it's just 2 wire links on that board, and it should enable us to have a ROM and RAM on that board, but still use the chips on the KIM-1. Here's the board in question. I've done the wire links at the back already. It feeds straight out. And this ROM out here, that's already programmed with the KIM-1 software. That's just the RAM chip, and you see we've only got the one IC there. So we plug this in and see what difference it makes. Okay, we're ready to go. Turn it on. Just reset. And we've got life. We've got life there. And we can step through. Code, etc. We're using this to drive the displays. It's got the timer as well, and some RAM that we're actually using at the moment. Then this IC over here is emulating these, and this chip is emulating the ROM that's in here. We just have to wait to see if that falls over. You may have noticed that it's not sitting on that marking out board anymore. It's now straight on a glass sheet. Oh, there we go, it's fallen over. And the glass sheet has stopped nearly all of that phase 2 jitter. So it's also doing the capacitance of that board. So it must be a very sensitive circuit. So I'm about reading the timing, the ROM from here, and whether that's causing it to crash. Well, we're not running on that ROM and we're still crashing. So I have improved the timing of this emulator greatly. The memory reads from this are a lot faster now, and the data's a lot more calm sitting on the data bus. But running with this ROM, which we know is a good one, we're still falling over. So I still don't know why we're falling over. I think I'll have to put the analyzer back on this. Okay, back to this setup, because the other one didn't prove anything at all. Let me start this up. One channel here on the phase 2, can't see under there. And these 4 here, with that wire out of the way. These 4 here are the signals to tell this where to scan on the keyboard and what display to use. And these last 3 are just picking up the strobe for these last 3 bits, so we can monitor them. Alright, let's rescan this. There we go. Scanning the keyboard and everything. All looks fine. See, there's all those zeros that were there before gone, and the phase 2 dropping is cutting right in the middle of the data nicely. And we've got to wait for that to fall over, see what happens this time. This is a complete crash, because here we are loading in the reset vector. Completely crashed. Been on this for like a week now. I still don't know what's wrong. It's the intermittent fault. I have noticed when it's a full crash like this that there's a lot more of those little glitches floating around. And if we zoom in on this one, which happens quite often, some of them are more than 1 sample long, like that one's 3 samples long, implying that there's some real data floating around here as well. And this is the signal going out to the selector for which 7-segment display to display and scan the keyboard. And the values going out from port B, basically, according to this, are changing. Well, port B should never be changing at this stage. Let's rescan that, see if we get any more, see if we see any other patterns. Assuming it's going round and round in the same circle. The process is actually running. It's just running the wrong code. Yep, I recognise all these addresses down here. So reset vectors pointing to a 0, which it runs and crashes. Where's those glitches? There we go. Funny little pattern again here. Actually, that's the same as the last one. A 2, a 1, 1 and 2. That's so the same pattern. It had a 4, not 3. So one of the others is, well, there's 2 channels doing exactly the same. I was wondering whether it was to do with like all these data bits have all suddenly turned off at once, and whether that's affecting the loading on the 74573 buffer chips, and it's bouncing the supply on them actually in the logic analyzer. Well, why should it go on and off? It's only the 1. I can understand 1, and it's too wide, and I can't capture this on the oscilloscope. Well, I've had another poke around with the scope, and I've got it internally on the logic analyzer, and you can see this spike here. That is the little spike we're seeing. This is data coming in normally, and this here will be enough to trigger it. I'll put it down to looking for a pulse less than 50 nanoseconds across, and that's the one that's triggered it. So all these little odd spikes, these ones here, little dips, and sometimes they go up, that's all internal on the logic analyzer. That's not on the data at all. And that's I'm not sure how to do that. I need some sort of filtering. Need to stop there's some sort of like ringing going on here before that. If I move that over, there's a whole long string of 1s coming in. There we go. So that's the data being read in. This data is coming from the lower 8 bits. So that would have been the data bus was reading there. And this is another one further up, internal to the logic analyzer. They go onto the same bus, but alternate between them. We're reading it there on the data 0, but sometimes it comes up on other one, if we go back to the screen here, you see there's all in a line here through the data, then they reappear here, because 0 to 7 on Logic Analyzer is the same pins on the internal bus as 16 to 24. If you look at the bits on here, 16 being the first one, no change on that, but you get that one's dropped, that one's dropped, this one's dropped, this one here is probably that one there. They tend to repeat. Let's run it again, see what we got. At least we know where those little glitches are coming from. It's nothing to do with the KIM-1. A whole bunch of them here. So here the address bus has gone down low, and we got some there. That's quite wide, those ones. I'll need to try and filter that somehow to make the analyzer a bit better. Oh well, at least we know what the glitches are. Okay, I've modified the Logic Analyzer software to have a sort of a pre-trigger on it. So if I select this pre-trigger button, it will start running and it will scan 32 channels at 4 MHz, and it will keep scanning around and around and around until it sees channel 31 go low. When that goes low, it will complete that scan and then save the data and send it out. I had noticed that very often when I've got the new 6502 plugged in, that the code will somehow jump to the other RIOT chip, the 003 RIOT chip. So I'll set the trigger to monitor that signal. So when it goes to there, which I managed to get it to do repeatedly, I can see what's happened a little while before then. I've done this a few times and it seems to foul in a very similar place each time. I've just triggered it again, and if we load the data in, it's not always failing exactly the same place, but it's failing in similar ways. Let's see where we are here. So that should be 9. It should switch to 9. There is a timer loop in the software. You find the right place in the software. Where are we? It spins around and around, decrementing the Y instruction. Here we go. This is a common place for it to foul. There's a 500 cycle delay between updating the displays, and it very often fouls at this point here, I found. When it goes to do this decrement here, it loops around here 127 times, according to that number there. Then carries on. Although it does this loop every time, you expect it to fail at this point quite often because it's running this bit of code for the majority of the time. Whenever you're delaying here between, oh, where are we? So there's delays running here. It's also running here, and it'd also be running for the 8, but it happened to fall over while doing the 8. Had it fall over in several places. It always seems to fall over in the same way. So if we zoom in here and see what it was doing, and it's coming through the code here. This so we've got 1F5D. Look on here, we've got 1F. There's C, D, so that's FD. That should be loaded in, and we get FD, which is the last bit of the branch if not equal, and then we got 1F5E, which is 1F5E, which is E8, which is increment. Oh, well, it would be increment. It's preloaded that. So 1F5E, the E8, but because you've got a branch if not equal, this is like a prefetch. It ignores that and goes back to 1F5B. Which we'll see is 1F5B is we've looped back round here. We should be loading an 88. So 1F5B, there's your 88, delivered onto the bus nice and early, strobed in at this point. Then we've got 1F5C next, which you'd expect. So 1F5C is D0, which is part of your branch if not equals, but it doesn't happen. We stay at 88. And it sticks at 88, and the program counter's counting up quite merrily, as it would do. There we go, going up and up, and then for some reason at this point here, the bus changes to 0. And then goes on, then it goes back to 88. And then we've got lots of ons and offs for some reason. And we've got 0, 74, 0. And it just starts doing random things. The data bus is all over the place. Did notice, if we look back at this one here, we look up at what the data bus is doing, the bottom addresses seem to stick. Mind you, at this point here, they've all stuck at 0. They seem to, the bottom bits stop working. Well, to be honest, I think it might be all the bits stop working, and then here, for some strange reason, it bounces all over the place. And then at some point, the code runs on and goes into the code for the 003 RIOT chip and starts getting some really strange addresses up here that it's running at. Because the address decoding repeats up through the memory map, this is triggering the second RIOT chip. And at some point, it will, we can find it. Is it going to show it on here? See if we got it here. No, it's still doing funny stuff. But it does eventually get to a point where it's running, scanning around a bit of code, which isn't crashing at all, but it's just pure chance it fell there. So for some reason, the data bus stops working at that point there. We can try and trigger that again, so I'll press the reset button. And if we re-trigger again, when you expect with the code here as 00 on a data bus that this would hit a break command. But it's if the CPU is not reading it in. You're getting the addresses here incrementing, but the data's, surely that would say, oh, I've got a break command being a 0, and then call the interrupt vector, but it doesn't. There we go. And that's finished loading. Okay, reload. Let's have a closer look, and we had where are we? D. This one looks a bit different. 5C, 5D, E, back to B, C, D, that's the loop. So at 5. Yeah, we're jammed at 5D, aren't we? So 5C should be DO. 5C is DO. And 5D should give us FD, which it does. And then we've got 5E. We should get, I know we're not going to run the 5E code at 5E unless we the counter had run out. So we'd have at least we'd have a E8 on the bus, which we don't. And it goes to, well, here we go. The bus doesn't change. It's done its decrement. It's done its branch if not equal. The branch if not equal has worked. So that would have been ignored, and a bit of data on there would have been ignored. 5E, and it's bounced back to 5B, as you expect it to, for the next loop. It should get an 88 on here. And we haven't got the 88. And we've gone on to 1F60, which is running further down. But we've got a 00. So why hasn't it executed that 00 and hit a break? So after much testing, this is what I've found. I seem to have found out what is causing these displays to go off. If we do the reset, so it's running. Okay, and now we do a scan on that. See what it's doing. We load that in. Now this is your normal scan. And if we've got the display segment 5, 6, or 7, should be 8 after that. We might have, no, it hasn't crashed. This bit's missing because of something in pulse view. It doesn't matter. We look at this one, number 6. We just zoom in here. Right, where are we? There you go. It reads the keyboard, etc. And then when we get to here, 1742, it then writes the value, in this instance, OF out there. Now, if we ignore the bottom bit, because we're using bits 1, 2, 3, and 4, not bit 0, we cover that up, you'll see there's a 7 going out, which is what we're getting out here. This bottom row is the bits coming out of port B to drive the decoder chip that does the strobing around the different 7-segment displays. So this is correct. Now we go back again. Oh, we see we've crashed. So if we just sample again. And we run this up, trigger it again. So this is while we're in the, I believe, the half crashed state, where the processor's still actually running, but there's no display. We bring that up. You can see that the port B is sitting at FF, or sorry, just F all the time. It's got the 4 bits are on all the time. We zoom into the similar place where we were before. And here we go, we've got 1740 is where we read port A, a couple other bits it does, and then it's writing out at, oh, which those pop-ups disappear. 1742, which is port B, is writing out a B out of there. So ignoring the bottom bit, that gives us 0101, which is 5. We should have a 5 coming out here. And we haven't, we've got F instead. So we write into port B, but nothing's coming out, and port B is stuck at 1111 all the time. So it's selecting output 15, which is nothing, so nothing is turned on. And let's mod something in the software on there. I'll have to turn it off to be able to do that. So here in the actual software that's running in the clone RIOT chip, there's a bit up here, right when we start up, where we turn all the pull-ups on for, it says port B. Port B on the microcontroller is port A and B on the KIM-1. So if we change this now, we get rid of that one, and we make it so we've got it, we'll put port A, we'll do as pull-ups, and port B, we'll do as pull-downs. The bottom 8 bits of port B here is actually port A on the KIM. So, pull-ups on port A, pull-down on port B. And we'll recompile that. When that's compiled, we'll just plug in the programmer, get it around the right way. Oops, cameras will be off. And program it. We can't see the program listing, it's off screen. And there we go. Let's plug that back in the main board. Alright, make sure it's around the right way. Push it in and we'll turn it on. Reset. There we go. Running. Just got to wait, see what happens now. Take a scan while it's running. There we go. Now load the data in again and see what we got. There we go. We can see the scanning of the digits and the keyboard. Okay, it's just crashed. It's see what we got now. And we've got Oh, there we go. So the output on port B is now just zeros instead of FF, or F rather. So if we can find out exactly where it starts writing out. Where are we? There we go. 740 is the read. And there we go. 742 is right to port B, and it's writing a D, so that'll be, we'll say it's 4, 5. It should be writing a 6 out when we're getting 0. So we got rid of those pull-ups, now pull-downs, and we just got 0 on those 4 pins coming in. So that kind of proves we've switched to an input. Now we've got to find out where it's switching to an input. In the software, where are we? So here we got a reset sequence. So when there's a reset come in, it's scanned in a few places. There's this bit here when it's waiting for phase 2 clock, and when it's got a phase 1, it goes on through the software, and it scans it a few more times in a bit of spare space, bit of spare time. And if port F goes to 0, which is the reset signal coming in, it will go back up and actually run that reset code. And the reset code is, it puts the port A and B back to inputs, which is what you expect if you're starting up from scratch. And it sets the data bus to tri-state as well, and then goes down to start watching for the phase 2 clock coming in and out. So if I comment out these to stop it running. So if we stop it from putting port B to an input, and we make it so those goes to an output all the time on KIM port B 1 to 4, then hopefully it'll keep the display going. This bit of code up here is what it does is it reads the address space at the bottom of the right chip RAM and adds one to it and puts it back. So if the display's running, we can actually check to see if this increments, and then we know how many times we've actually come back through this bit of reset code. And we've just got to program that up. Okay, let's plug back in. See what we get this time. Turn it on. Just to reset. And we got some stuff there. Right, so we go to 17C0. That's the bottom RAM address. And there should be a number in there. Just to reset, you'll see it keeps changing. See if we can get it to 0. There we go. We'll leave it at 0. If we see that count up to 1, then we know we've run through that reset code. Oh, there we go. That means we've run through that reset sequence at least once. There's no external resets happening. I've had the scope of that on there, and there's just nothing happening on the KIM board at all. It's just local to that clone RIOT chip that's getting that reset signal. I'm not sure if I need it at all. I might just get rid of the whole thing. So now we've got this sort of working with the ROM and RAM board plugged in. Maybe we can get rid of this board and just run it on the ROM that's in the RIOT chip tucked in here, and see if that works okay. Well, we're sort of running, but we're still getting crashes, but just total crashes now. Fix the display, at least that's going. I've just got to find out what is making it completely crash. Hopefully I haven't got to spend as much time on it for this fault as I for the last one. I spent at least a week on this. If you're still with us, don't forget to put lots of comments below. And don't forget to like and subscribe. And hopefully I'll see you in part 12.